Alright, in this video we're going to look at solving trig equations. So a trigonometric equation is one that contains a trig function with a variable such as sine of x equals a half. So if we take a look at the graphs of the left side, sine of x, and here on this graph sine of x is the blue graph, and the red horizontal line is the graph of y equals a half. Notice that if it hits the graph once, if it intersects the graph once, it's going to intersect it an infinite number of times. We saw that with inverse trig functions as well. So with trig equations, if it hits it once, because of the periodic nature of the graph, it's going to hit it an infinite number of times, which means there's going to be an infinite number of solutions. So the general form of our solution is x equals pi over 6 radians, which is right here. And then because of the period of the sine function is 2 pi, it's going to be every 2 pi radians thereafter. So pi over 6, and then every 2 pi radians both going to the right and going to the left. So all we have here is nothing more than a sequence rule. In fact, it's an arithmetic sequence with the common difference of 2 pi for the period of the sine graph. Likewise, we also not only hit the graph each wave on the way up, we also hit it again on the way back down at pi over 6 radians, or 150 degrees. In addition to hitting it at 5 pi over 6, we also hit it at 17 pi over 6 and multiples of 2 pi the other direction as well. So we also hit it at negative 7 pi over 6, which is 5 pi over 6 minus 2 pi. So here we have a second arithmetic sequence with a common difference of 2 pi. So 5 pi over 6 plus multiples of 2 pi thereafter. And again, keeping in mind, the period for sine, cosine, secant, and cosecant is 2 pi. For tangent and cotangent is only pi. Now, since there are going to be an infinite number of values that these sequences are going to generate, we're going to confine our answers to be between 0 and 2 pi, or within one rotation of from between 0 and 2 pi. So how to solve a trig equation is get the trig function by itself if possible, just like you'd solve any equation for x by trying to get x by itself. And then solve for the variable. You can use inverse trig. You can look down the chart for the values as well. So let's take a look at a couple examples here. First up, we're going to solve each of the following in the interval 0 to 2 pi, where we will include 0, but we won't include 2 pi. So we're going to start with the cosine of 2x equals negative square root of 3 over 2. Now, I recommend working with degrees, getting your answers in degrees, and then just converting them to radians. You don't have to do that, but if it helps, then all the better. So what we want to start with is we have cosine here. Don't worry about the 2x for now. We want to know all the angles between 0 and 2 pi, or let's stick with 0 and 360, all the angles where the cosine is negative square root of 3 over 2. Well, there's two angles where the cosine of the angle is negative square root of 3 over 2. That's at 150 degrees and 210 degrees. Don't worry about this other stuff for right now, but cosine 150 is negative square root of 3 over 2, and the cosine of 210 is negative square root of 3 over 2. Now, we're not taking the cosine of x, we're taking the cosine of 2x. So 2x is going to equal 150 plus every multiples of 360 degrees. And 2x could also equal 210 plus multiples of 360 degrees. So here I'm just working with degrees because I can always change them back to radians when I'm done. If I didn't want to do that, I'd have 2x equals 5 pi over 6 plus 2 pi n, and 2x equals 7 pi over 6 plus 2 pi n. Either one's fine. So we got to get x by itself. So if we divide both sides by 2, we get x equals 75 plus 180n. Here we get x equals 105 plus 180n. Don't forget to divide the 360n's by the 2 as well. So now we can generate each of these arithmetic sequences here. We can generate a list of angles and make sure that our angles are between 0 and 360 degrees, not including the 360 degrees. So let's start with our first one. We can start with 75. That's between 0 and 360. If we add 180 to 75, we get 255. That's between 0 and 360. But if we add 180 to 255, we get 435, which is not between 0 and 360. So we don't want to go beyond 255 degrees. Likewise, we also don't want to subtract 180 from 75 and go this way because that'll be less than 0, and we don't want it to be less than 0. Over here for this other equation, we'll start with 105. That's between 0 and 360. If we add 180 to that, we get 285. That's also between 0 and 360 degrees. But if we add another 180 to that, we're going to get 465 degrees, and that's not between 0 and 360. Likewise, if we subtract 180 from 105, we're going to be less than 0. So we have 4 angles between 0 and 360 that make this original equation true. So all that we have to do now is just write each one of these angles in their equivalent radian form. And 75 degrees is 5 pi over 12, 105 is 7 pi over 12, 255 is 17 pi over 12, and 255 is 19 pi over 12. Now, a trick that I use for coming up with this list quickly rather than convert 4 separate ones to radians is if we find the greatest common factor of 75, 255, 105, and 285, the greatest common factor is 15. 15 degrees in radians is pi over 12. So 75 is 15 times 5. So 75 degrees should be pi over 12 times 5, which is 5 pi over 12. 105 degrees is 7 times 15 degrees. So again, 15 degrees is pi over 12. It'll be 7 times pi over 12, which is 7 pi over 12. So that's just a quick little technique you can use to help you make shorter work of your listing out your angles. All right, part B, we have cosecant of 1/3 x minus pi equals the square root of 2. Let's ignore what's in here and look down our list to find what angles give us a cosecant value of square root of 2. It's 45 degrees and 135 degrees. So now we can worry about the 1/3 x minus 180. We'll convert it to degrees. So we have 1/3 x minus 180 is 45 degrees plus 360 n. Again, this 45 degrees is because cosecant of 45 degrees gives us square root of 2. We also have 1/3 x minus 180 degrees equals 135 degrees plus 360 n. Again, this 135 comes from the fact that the cosecant of 135 degrees also equals the square root of 2. So we'll work with each one of these. We'll first add the 180 to both sides. So we're going to add 180 to 45 in the first, and we're going to add 180 to 135 in the second. We get 1/3 x equals 225 degrees plus 360 n. And we also get 1/3 x equals 315 degrees plus 360 n. Now we can either divide both sides by 1/3 or multiply everything on both sides by 3. So if we do that, we get 675 degrees plus 1080 n. We also get 945 degrees plus 1080 n. Again, this 1080 degrees would be the period of this function if this were in degrees. So again, it's the what we have at the end here, this plus 1080 n, is the period of this function here on the left. So going back to graphs of other trig functions. However, when we start listing out values, 675 and 945, we'd have to subtract 1080 from them to get back between 0 and 360, but we're not going to get any angles between 0 and 360 by doing that, nor are we going to get any angles between 0 and 2 pi. So as far as restricting ourselves to be between 0 and 2 pi, there are no angles between 0 and 2 pi that will make this original equation true. All the other ones are outside this range of value, this interval of values. All right, part C, cotangent of 3x equals 0. Well, let's look down our list. Where's cotangent equal to 0? It's equal to 0 at 90, and it's equal to 0 at 270. So a little bit like the first one, we're going to have 3x equals 90 plus. The period of cotangent is only 180, so please keep that in mind, that tangent and cotangent, remember, their period is 180 degrees, or pi radians. So we have 3x equals 90 plus 180n. We have 3x equals 270 plus 180n, because the cotangent of 270 degrees is also 0. Dividing everything on both sides by 3, we get x equals 30 plus 60n for our first one. We get x equals 90 plus 60n for our second one. Again, the period of cotangent of 3x, that period is 60 degrees. So listing this out as our first one for our sequence, we have 30 plus 60 is 90, plus 60 is 150, plus 60 is 210, plus 60 is 270, plus 60 is 330, plus another 60 is 390, which is not between 0 and 360, so we can stop. For our second one, we got 90, and then add 60 to that, we get 150. Add 60 to that, we get 210. But notice we're just generating this exact same sequence as we got in the first one. And that's a property of tangent and cotangent because their period's only 180 degrees. This second sequence is just going to be the first sequence with repeated values. So we only really, for tangent and cotangent, need to list out the terms of this of one of the sequences, and we'll have them both. So converting all of these to radians, which we also have on our chart, here are our 6 angles, for example 1C, in radians. All right, that about does it for this video. Thanks for watching. I'll see you next time.